Alright guys, how's it going? I often get asked my opinion on various topics, including obviously tech related, but also political and scientific subjects. And one that turns up every so often is the topic of global warming. And it just so happens that back in 2010 I spent a year studying this, and other related subjects, at the Open University. Now I had no intention of pursuing a career in the field, I simply wanted the knowledge. It was an eye-opening and mind-opening course, and in this video I'm going to share with you the important details, the facts and the figures. So this is something slightly different for the channel, so let's get on with it. So we'll start off with what is global warming. Put simply, global warming is the process of the Earth's atmosphere heating up over time. You've all seen the headlines, the melting ice caps, the increase in hurricanes, all that stuff which invariably gets lumped under the clickbait title of global warming. One problem with this though is that in many cases of the extreme weather that we see, we just don't know if it's down to global warming or if it's just the weather being the weather. We know that hurricanes, tornadoes, they've been around for hundreds of years and almost certainly thousands and millions of years, so there's no need for us to attribute what we see today as being down to global warming. But what we can do is compare historical temperatures, historical levels of greenhouse gases, compare those to the recent temperatures and current levels of greenhouse gases in the atmosphere while noting the trends. Before that though, I'm going to start with a topic that almost everybody will have heard of. That is the greenhouse effect and the greenhouse gases. Starting with the greenhouse effect, up at the top left we have the sun, our home star which powers the climate system on Earth and on every other planet in the solar system. Everything starts with the sun. It is the source of almost all the energy and all of the life on Earth. And here we can see solar rays, about half of which gets absorbed by the Earth's surface and warms it up. We can all see this in a hot day. Put your hand or your bare feet on tarmac and you can feel the heat. But some of the sun's rays are reflected by the Earth and the atmosphere as well. Stuff like clouds, basically reflected off into space, never to be seen again. But the solar rays that reach the Earth, warming up the Earth, are then emitted from the Earth's surface as infrared. Some of the infrared radiation does actually pass through the atmosphere, so the infrared just shoots off into space, the same as the solar rays, but most of it is absorbed and re-emitted in all directions by clouds and greenhouse gas molecules. The effect of this is to warm up the Earth's surface and the lower atmosphere. And it's safe to say that the greenhouse effect gets some pretty bad press, but in fact, without a greenhouse effect, the Earth would be a frozen rock, because all of the infrared radiation would escape the atmosphere and there would be no heat being held in the atmosphere and on the surface. So the greenhouse effect isn't bad, it is in fact a requirement for life to exist on Earth. But what about greenhouse gases? Now here's a pie chart of the composition of Earth's atmosphere, completely dominated by nitrogen at 78% and oxygen at around 21%. The combination of those two is 99% of the Earth's atmosphere. And then you've got argon at just under 1%, all other gases less than 0.2%, and possibly the most famous and much maligned atmospheric gas, carbon dioxide, languishes way down at 0.03%. Now obviously carbon dioxide is a very newsworthy gas, the most famous greenhouse gas, but this isn't due to volume, as there is more water vapour in the atmosphere, and as you will now see, water vapour is also a greenhouse gas. But how do we know which gases are greenhouse gases and which ones aren't? There's actually a pretty simple rule for it, which I will now explain. So this is a single atom of argon, and as you just learned, argon is less than 1% of the composition of the atmosphere. And argon exists as this single atom in gas form in the atmosphere, and it is not a greenhouse gas. Now moving on to atmospheric nitrogen, N2, and it is simply 2 atoms of nitrogen. This here is the main constituent of our atmosphere, and like argon, nitrogen is also not a greenhouse gas. Now moving on to oxygen, or the oxygen gas in our atmosphere. Like nitrogen, the oxygen gas molecule comes as a pair of oxygen atoms, and also like nitrogen, it is not a greenhouse gas. And now we have carbon dioxide. 1 carbon atom, 2 oxygen atoms. And as mentioned previously, carbon dioxide is a greenhouse gas. And this is the first rule of what is and what isn't a greenhouse gas. Any molecule which has more than 2 atoms is automatically a greenhouse gas, including water, 1 oxygen, 2 hydrogen, H2O. Water vapour in the atmosphere is a greenhouse gas because it has 3 atoms. Nitrous oxide, clearly a greenhouse gas, 2 nitrogen, 1 oxygen. But what about carbon monoxide? One carbon and one oxygen. Is this a greenhouse gas? And the answer to that is yes, it is also a greenhouse gas. It's a very weak greenhouse gas. It does have less than 3 atoms. However, so long as the atoms are of different elements, then the gas will be a greenhouse gas. So nitrogen, because it had 2 nitrogen atoms, not a greenhouse gas. Oxygen, not a greenhouse gas. Carbon monoxide, a greenhouse gas. And all of that is basically the simple rule for what makes a greenhouse gas. You may be wondering about the exact mechanism behind it. It's a little bit beyond the scope of this video, but in a nutshell, these bonds that we can see here in this water, it's actually more like a spring bonding the atoms together, and this allows the infrared radiation to be absorbed by the molecule, causing the molecule to rotate and or vibrate, and this only happens with the greenhouse gases. So that's pretty much the greenhouse effect and the greenhouse gases explained as simply as possible. But let's get back to global warming. How do we know that the Earth is warming? Well, we're recording the temperatures, and temperatures have been getting recorded since the 17th century in central England. Now you might be thinking, well, how accurate can 300, 400 year old temperature readings be? And that is a fair point. However, from the mid-1800s and onwards, the GMST, that is the global mean surface temperature, has been recorded with a far more methodical scientific approach. Thermometers and other weather measuring instruments have been placed at locations worldwide in these Stevenson screens. These little square boxes, which were designed to measure temperature, but notice the slats, it doesn't allow direct sunlight or exposure to wind and rain. These were invented by a fellow Scot called Thomas Stevenson, who is also the father of the famous author Robert Louis Stevenson of Treasure Island fame. So if you've ever seen one of these by the side of the road and wondered what it was, now you know. Now these numbers are simply not in any doubt. So if you're wondering if the Earth is actually getting warmer, you can stop wondering. The Earth is definitely getting warmer. Temperatures have been accurately measured for around 150 years all over the Earth. And here we can see one from NASA, and we can see on the left hand side the temperature anomaly in Celsius, and the trend is crystal clear, especially since the 1960s and onwards. The global mean surface temperature just continues to rise and rise. This is based on land and ocean data. If you just look at the land data only, again we can see the clear trend line towards higher and higher temperatures. Looking at the left, 1880 minus 0.5 to what is now plus 1 degree. That is 1.5 degrees difference in temperature at the exact same spot on Earth, measured at the same time every single day for almost 140 years. And the constant trend of the rise in temperature is clear to be seen. The surface of the Earth is getting warmer. Okay, so the Earth is heating up and it is crystal clear. But we know that the Earth's temperature cycles between hotter and colder periods over hundreds of thousands, even millions of years. And we know this from looking at ice cores at the Vostok Research Station in the Antarctic. 3-kilometre long cores of ice drilled out of the Antarctic ice sheet. And this alone is absolutely fascinating. On the y-axis is the delta in temperature in degrees Celsius, while the x-axis is the age in thousands of years. So what you're looking at here is the history of the Antarctic temperature over the last 400,000 years or so, and we can clearly see the peaks where the temperatures are higher, which appears around every 100,000 years. These are known as interglacial periods because in general temperatures are a lot lower than during these peak periods. The cause of these peaks is due to the Earth's orbit around the Sun and also the tilt of the Earth's axis. This cycle will be repeated again, and as you can see on the chart, right now we are in one of these interglacial periods. Generally speaking, the Earth is a lot colder than what it is right now, and this has led climate change deniers to suggest that the current increase in the Earth's temperature simply comes down to the Earth's orbit and the natural cycle. So what's the big deal? Yes, the Earth is getting hotter, but we're in that part of the cycle where the Earth heats up anyway. Well, getting back to the greenhouse gases, and especially carbon dioxide, here we can see the percentage of 0.03%. When dealing with small numbers like this, rather than writing it as a percentage, it's more often written as parts per million. So in the case of carbon dioxide, rather than 0.03%, this would be written as 300 parts per million. In other words, there are 300 carbon dioxide molecules in every million parts of air. And since the late 70s, the amount of carbon dioxide in the air has been measured, in particular at the Mauna Loa Observatory in Hawaii and also again at the South Pole. So take a look at the levels of carbon dioxide in the atmosphere over the past 30-40 years. Now we can see instantly, January 1979, the level of carbon dioxide in the atmosphere was measured at 336 parts per million. And you'll instantly see that the levels of carbon dioxide in the air increase and decrease over the year. And this is really quite fascinating. If you just concentrate on the red dot at Mauna Loa, the CO2 rises to a peak in the early part of the year before falling mid-year and then rising again towards the end of the year. But the opposite happens at the South Pole. I'll touch on that point later on. For now though, just continue to watch as the levels of atmospheric CO2 continue to rise month after month, year after year, decade after decade. In only 10 years, Mauna Loa had surpassed 350 parts per million, never to drop below that since. And looking at the bottom right, the rise and rise of atmospheric CO2 is clear to be seen. Just as there is no doubt that the Earth is warming, there is also no doubt that the levels of atmospheric CO2 is also rising. And this is the basis of the argument for global warming proponents, who claim that the reason the Earth is heating up today is based on the rapid increase of atmospheric CO2, and it simply continues to rise and rise before we go back in time. The green line is Achillean data between 1958 and 1979, and from that data we can also see the continued rise of CO2 in the atmosphere. And you remember how we checked the Vostok ice core for temperatures? We can also check ice cores for levels of CO2 or any other gas. The reason these ice cores are so useful is that the composition of air at that point in time gets trapped in the ice. So we really are looking at a snapshot of the Earth's history at that time. And going back to pre-industry, before the Industrial Revolution, atmospheric CO2 was around 278 parts per million. And all the way back to 0 BC, we never saw atmospheric CO2 above 300 parts per million. And on checking the Vostok ice core, going back tens of thousands of years to the ice ages, we see even lower levels of atmospheric CO2, rising every 100,000 years or so. Does that pattern look familiar? It should, because it is very, very similar to the Vostok ice core temperature pattern, as you can see here. And even going further back to 800,000 years ago and the West Antarctic Epica ice core, we can see a similar pattern. When I first dug out this slide, I knew it must be quite an old one because the carbon dioxide was 0.03% or 300 parts per million. But today the atmospheric CO2 levels are above 400 parts per million and still rising. So I've decided to update the pie chart. So that last 2.5-3 minutes covered quite a lot of ground. So let's just take stock of what we saw there. First of all, we saw the rising and decreasing levels of CO2 during the year. So what's that all about? Well, some climate change deniers believe that we are simply too small to have a large effect on the Earth's atmosphere. All the CO2 that we pump into the air is not enough to have an effect. But what we can actually see here is the effect of photosynthesis, trees taking carbon dioxide from the atmosphere to be used as energy. Now obviously photosynthesis is more active in the summer because plants and trees have more leaves during the summer. So this is why the levels of carbon dioxide in the northern hemisphere start dropping during the summer months, and then the CO2 levels begin to rise again during the later months when the trees have less leaves and are performing less photosynthesis. And the opposite is seen in the southern hemisphere because, as you know, in the southern hemisphere, winter is summer and summer is winter. We can see this in the CO2. The trees are actually photosynthesizing at different rates in the north and south hemisphere. Meaning as the northern hemisphere rates rise, the southern hemisphere rates fall. But you might think that humans can't be having an effect on the Earth's atmosphere, but every single year it is clear to see that the trees are having an effect. The same cycle continues every year, the only difference is the average levels of atmospheric CO2 continue to rise and rise. And if it's not humans causing it, then where's it coming from? The second major point here was again what we saw in the Vostok ice core. If you remember the temperature graph where we discussed before that in most cases the Earth was much colder than it is today, while having interglacial peaks every say 100,000 years or so, and that we were in one of those peaks right now. And we saw a very similar pattern with the CO2 data, generally a lot lower, rising to peaks every 100,000 years. And there is the comparison chart. Temperature in red, CO2 in blue. The correlation is very, very clear. And again, when superimposed, we see CO2 and temperature tracking very closely. Just look at what has happened recently though. But sticking with this, in actual fact, in closer inspection, it was discovered that the temperature rise happened first. As the ice ages were coming to an end, the temperature rose first, followed by a rise in carbon dioxide. Now obviously the global warming proponents, their entire claim is that the carbon dioxide in the atmosphere is causing the temperature rise, but what we saw in the ice cores was the opposite. The temperature rose first, followed by the rise in carbon dioxide. Now obviously this data was met with great enthusiasm by climate change deniers, who of course claimed that this was proof that carbon dioxide was not responsible for the current increase in atmospheric temperature. And there were many articles, many scientists claiming this was a nail in the coffin for the proponents of global warming. But in actual fact, carbon dioxide following temperature rise makes perfect sense. And this was actually predicted back in 1990, almost 30 years ago, in a paper by Laureus. Essentially what is happening here is, if you remember when I talked about the Earth's orbit affecting ice ages, so for example, the further away we are from the sun, the colder the planet will be. It's not just based on that, it's also based on the actual tilt of the Earth too. But it goes in a cycle, and at the beginning of every cycle, for example, when the temperature starts to rise, this occurs due to the change in orbit and the change in actual tilt, and the planet starts to heat up. And what happens when the planet starts to heat up? Well, first of all, the ice starts to melt, and we already know what is held in the ice: carbon dioxide and other greenhouse gases. Even more importantly, as the oceans begin to heat up, they also give off more carbon dioxide. We can see here that when water is heated, the carbon dioxide is driven out, and you can check this by using 2 cans of soda. The warmer can will fizz more when opened, because it is letting off more CO2. The same thing happens in the ocean as the oceans are heated, adding more CO2 to the atmosphere. And as more CO2 is added to the atmosphere, the Earth gets warmer, and as the Earth gets warmer, the poles continue to melt, releasing more CO2 into the atmosphere, and the Earth gets warmer. And this is why the rise in carbon dioxide appears to lag the rise in temperature. What's actually happening is there is an initial rise in temperature from the changes in the Earth's orbit around the sun and the axial tilt. But this initial rise in temperature, which starts melting the ice and starts heating the oceans, causes carbon dioxide to be released into the atmosphere, which then begins a feedback loop, causing the temperatures to rise and rise and rise over 100,000 years. So far from being a nail in the coffin of global warming, it actually adds to the evidence of what we are seeing today. Now, a lot of climate deniers point to periods in the past. For example, the Paleocene-Eocene thermal maximum, which happened 56 million years ago. This is one of the hottest periods in Earth's history, and the average temperature rose almost 6 degrees over a period of about 20,000 years. In fact, we think it was maybe 6 degrees over 10,000 years, or maybe even 8 degrees over a period of 10,000 years. And this was the most rapid documented warming in the past. So let's be generous and say 8 degrees over 10,000 years. That would be 0.8 of a degree over 1,000 years. And yet the numbers I used from NASA earlier, we saw it was over 1 degree in not much over 100 years. So compared to this hot event that some climate change deniers use as a reasoning for why global warming isn't man-made, the fact is, comparatively, right now the Earth is heating almost 10 times faster than during this thermal maximum period. And this is one of the simplest points. Proponents of global warming never claimed that the Earth wasn't hotter in the past, and they never claimed that the Earth didn't cycle between hotter and colder periods. But one of the claims has been that the rate of change in the temperature has increased to a level that has rarely, if ever, been seen before in the history of the Earth. The figures go between 5 and 10 times faster. Based on our temperature records of the past 100 years, and especially from the past 50 years, from maybe around the 1970s, we are heating up the Earth at an unprecedented rate. From the geological record, we can see that there were times in the past where the Earth did heat up at the same kind of speed, but these rapid warmings appear to have been the result of catastrophic change. For example, mega volcano eruptions and that kind of thing. And another important thing here about this Paleocene-Eocene thermal maximum was that our current rate of carbon release to the atmosphere is almost 10 times higher than the highest rate during this time, which suggests that we are altering our environment in an unprecedented and unpredictable way. It's true there were also times in the past where levels of carbon dioxide were far, far higher than what they are today, but this was a gradual change taking place over millions of years, giving the ecosystem time to adapt. One obvious example of this would be during the Carboniferous period of between 300 million and 350 million years ago. At some parts of this, levels of carbon were double what they are today, 800 parts per million. Atmospheric oxygen was also 50% higher as well. The reason for this was the Earth was blanketed in swamps and trees, so the trees could take in a lot more of the carbon dioxide and give it off as oxygen. Obviously, photosynthesis is when the trees take the carbon in, and respiration is giving off oxygen and also carbon dioxide. The difference here was this took millions, tens of millions of years for the Earth to evolve to this state, and temperatures are the same as what they are today. So how is that possible? All that carbon dioxide in the atmosphere, and yet the temperature remained the same, which is another argument used by global warming deniers. The difference here is 350 million years ago, the sun was releasing less energy. The sun is like any other star. As it gets older, it gets hotter. 300 million years ago, the sun would be giving off less energy, so the Earth would be colder anyway. As you can see, it's not always as simple as looking at the numbers. The problem we have here today though, is that the sun is older, the sun is giving off more energy, and all these dead trees from the Carboniferous period, the coal that we are burning today, releasing into the atmosphere, is not being taken up by the trees, it is not being turned into oxygen in the way that it was back then. The big problem we have today is we are in a feedback loop where we release more of this carbon back into the atmosphere, but there aren't enough trees to deal with it. And we can see the results of this because the ice caps are shrinking. You remember the first slide where we saw that some solar radiation is reflected by the Earth and the atmosphere. And I mentioned that clouds could reflect solar rays. Something else reflects solar rays, and that is ice. In particular, the polar ice caps. This one's simple to understand. Lighter materials reflect light, darker materials absorb light. That's why people wear white t-shirts during warmer days instead of black ones. But if the ice caps are melting, and the ice caps are melting, then that is even less solar rays reflected away from the Earth, which means even more infrared radiation being absorbed by the greenhouse gases in the atmosphere, which causes more heat, which causes more melting of the polar caps. What we are doing to the Earth is not natural. This is not a natural event. This is caused by us putting the carbon in the Earth back into the air where it shouldn't be. Right, so this video took quite a while to get out, as you probably noticed. It has been a massive undertaking. I've been rereading my course materials from 7 or 8 years ago, and the more I looked at it, the more I realised that some of my information was out of date. Like everything else, global warming is a fast-moving area, but what I learned since then was even more fascinating than what I learned before. And as with everything else, there are of course counterpoints. This one's got some time to go yet, but for me, I firmly believe that right now, humans are causing unprecedented levels of global warming. I'm not all doom and gloom about it because there are ways that we can fix this. We can get that carbon back out of the air. It's going to take some time and it's going to take some will to do so. And for me, this is the important thing. We first of all need to get the agreement, and then we just deal with the problem of getting the CO2 back out of the atmosphere. And that way everybody wins. There is simply no need to risk it. There is nothing to be gained by having that CO2 in the atmosphere. Hopefully that is clear to everyone. But that's it for this one. If you're interested in reading up further, I'm just going to throw a bunch of links into the video description. Check out my Amazon links as well. Obviously, I'm really interested in what you think about this video. It's a little bit different from what I've been doing, but I do intend to do more of this kind of thing every so often. It's all science, it's all technology, it's all related as far as I'm concerned. And over time, tech, science, it'll all be the same thing. Don't forget to like and subscribe, and I'll catch you later, guys.